Hello and welcome back to my channel. Today we will be doing something a little bit different. We will be covering the whole of Year 1 Inorganic Chemistry for OCR A-Level. Let's start with Chapter 2, Atoms, Ions and Compounds. The atom is made from three types of subatomic particles: the neutron, the electron and the proton. Protons and neutrons are found in the nucleus. The proton has a charge of +1, the electron a charge of -1, and the neutron is neutral, so has a charge of 0. Nearly all of the atom's mass is in its nucleus, so we say that the proton and the neutron have a relative mass of 1. The electron is very tiny, so has a relative mass of 1/1836. So an atom's mass is the number of protons plus the neutrons. The atomic number is the number of protons. This equals the number of electrons. Every atom of the same element has the same number of protons, but the number of neutrons can change. Isotopes are atoms of the same element with the same number of protons but different numbers of neutrons and different masses. Isotopes have similar chemical properties as they have the same number of electrons, but they may have slightly different physical properties as they have different masses. In chemistry, the mass of an atom is very tiny, so we compare it to 1/12 of the mass of an atom of carbon-12. Relative isotopic mass is the mass of an isotope compared to 1/12 of the mass of an atom of carbon-12. Relative atomic mass is the weighted mean mass of an atom of an element relative to 1/12 of the mass of an atom of carbon-12. We can calculate relative atomic mass given an element's isotopes by timesing the isotopic masses by the percentage abundances. We find the total of all of these and divide by 100. An element is a substance made up of one type of atom. A compound is a substance containing more than one element, chemically combined and in fixed proportion. A binary compound is a compound containing two elements. A molecule is a group of atoms covalently bonded together, and an ion is a charged atom, an atom that's lost or gained electrons. We can figure out the charge in an ion by using the periodic table. Each column in the periodic table is called a group. Elements in group 1 of the periodic table have a charge of +1. Elements in group 2 have a charge of +2. This is because every atom wants to have a full shell of electrons. In group 1 of the periodic table, they have 1 electron in the outer shell. They need to lose this to have a full shell. Therefore, they've got a 1+ charge. On the other side, elements in group 6 of the periodic table find it easier to gain 2 electrons to get to a full shell than lose 6. Therefore, they have a 2- charge. Metals always have a positive charge and non-metals have a negative charge. We can find the charge of a transition metal by looking at their Roman numerals. Polyatomic ions contain atoms of more than one element bonded together. You have to be aware of a few polyatomic ions for A-levels. These include ammonium, hydroxide, nitrate, nitrite, manganate, carbonate, sulfate, sulfite, dichromate, and phosphate. Ionic compounds contain positive and negative charges. The overall charge for an ionic compound is 0, so the positive and negative charges must balance. For example, if you had a compound of magnesium chloride, you would see that magnesium has a 2+ charge and chloride has a - charge. You need 2 Cl- to balance out the Mg2+. Some atoms go around in pairs. These are called diatomic molecules. They include hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. When balancing equations, you must make sure that there's the same number of atoms on each side. On to Chapter 3, Amount of a Substance. The amount of a substance, or little n, counts the number of particles in a substance and is measured in moles. 1 mole contains 6.02 times 10 to the 23 atoms. You do not need to remember this number as it is on your data sheet. This number is referred to as Avogadro's constant, and it's the same number of particles in each mole of carbon-12. Molar mass, or big M, is the mass per mole of a substance, and it's measured in grams per mole. The molar mass of a compound can be found by adding together all of the relative masses found in the periodic table. We can use the equation N equals little m over big N. Moles equals mass over molar mass to find the number of moles in a compound. The molecular formula is the number of atoms of each element in a molecule, such as H2O, CO2, or MgO. However, the empirical formula is the simplest whole number ratio of atoms of each element in a compound. Given the percentage composition of a compound, we divide each percentage by the molar mass of every element to give us the number of moles, then divide the number of moles by the smallest number of moles found. This should give you a ratio of every element. You can use this ratio to find the empirical formula. Salts are ionic compounds made up of two groups of oppositely charged ions. Many salts are hydrated, meaning they contain water as part of their crystalline structure. This water is also known as water of crystallization. When the salt is heated, bonds holding the water within the crystal are broken and the water is driven off, leaving behind an anhydrous salt. This is why, to find pure crystals of salt, we have to heat to a constant mass. Another equation is N equals CV. Moles equals concentration times volume. It is important to remember that volume must be in decimeters cubed. If your volume is in centimeters cubed, you will have to divide by 1,000. Another equation is moles equals volume divided by molar gas volume. This is used to find the number of moles of a gas. At room temperature, the molar gas volume is 24 decimeters cubed. However, experiments don't always happen at room temperature. This is when we use the ideal gas equation. Here we make the assumption that the particles are in random motion, there are elastic collisions, the particles are extremely small, and they have no intermolecular forces. The formula is PV equals nRT. Pressure times volume equals number of moles times gas constant times temperature. The unit of pressure is kilopascals, the unit of volume is meters cubed, the unit of temperature is Kelvin. The gas constant is given on your datasheet. It is 8.314. You can rearrange this equation to give us the number of moles of a gas. The ratio of moles in an equation is called stoichiometry. When we conduct an experiment, we may not make the maximum amount of product, the theoretical yield. This is because the reaction may not have gone into completion, other side reactions may have taken place, or purification in the product may have resulted in some product being lost. We can express the conversion of starting materials into the product by using the formula percentage yield equals actual yield divided by theoretical yield times 100. We can use the yield in moles or in grams. The reactant that is not in excess is the limiting reagent. This must be used to figure out percentage yield. Atom economy is a measure of how well atoms have been utilised. Reactions with higher atom economies produce a large proportion of the desired product and few unwanted waste products, are important for sustainability as they make the best use of natural resources with limited waste. We use the equation atom economy equals mass of atoms in desired product divided by mass of atoms in reactants times 100. We tend to use the molar mass. On to Chapter 4. Acids and Redox. All acids contain hydrogen in their formula, and when dissolved, they produce hydrogen ions. We call this dissociating. Strong acids completely dissociate in aqueous solutions. Weak acids partially dissociate in aqueous solutions, and we often show this by using reversible reaction signs to show the reaction isn't complete. A base neutralizes an acid to form a salt. An alkali is a base that dissolves in water to release hydroxide, OH, minus ions. If an acid is neutralized with a base, alkali or metal oxide, a salt and water is formed. The salt is named after the acid and a metal/ammonium ion. For example, if we use hydrochloric acid, the salt will contain chloride. If we use nitric acid, the salt will contain nitrate. sulfuric acid, sulfate, and ethanoic acid, ethanoate. You should be aware of the formula for all of these 4 acids. The ionic equation for neutralization is H plus OH minus goes to H2O. The H plus comes from the acid and the OH minus comes from the alkali. Another reaction you should be aware of is an acid plus a metal carbonate goes to a salt, water, and carbon dioxide. A titration is a technique which accurately measures a volume of a solution that reacts with another solution. We can use them for finding the concentration of solutions, identifying unknown chemicals, and finding the purity of a substance. When we're doing a titration, we often use a standard solution. A standard solution has a known concentration. It is made in a volumetric flask and is measured very accurately. You will often be asked how to make up a standard solution. First, you weigh the solid, and then you dissolve the solid using a small amount of distilled water in a beaker. Transfer this solution to a volumetric flask using a funnel. Rinse the beaker and funnel with distilled water into the flask. Carefully fill the volumetric flask with water until you hit the graduation line. Invert the flask and mix your solution. Using the stoichiometry of an equation, if you know a lot about one reactant, you can find out a lot about the other. Here we use moles in our calculation. The moles equals concentration times volume will come in handy. Standard equipment for a titration is a pipette and a burette. Often be asked to calculate percentage uncertainty. To do this, we use the uncertainty given in a question. We divide that by the measured value and times 100. It is worth noting that for burettes, we take 2 values, the first and the second, to give our titra. Therefore, we must times the uncertainty by 2. Key tips for titrations. When filling a burette, run excess solution through to get rid of air bubbles. You must read from the bottom of a meniscus. Do a trial run to find an approximate titra. This shouldn't be included in your final mean. Calculate your mean using only concordant titras. Concordant titras are within 0.1 centimeters cubed of each other. Redox stands for reduction and oxidation. Reduction is gain of electrons. Oxidation is loss of electrons. You may have seen this at GCSE wrote as oil rig to help you remember. Oxidation numbers are assigned to different atoms and can be thought of as the number of electrons involved in bonding. Pure elements have an oxidation number of 0, as do diatomic molecules, such as H2. Most oxidation numbers can be found using the periodic table. For example, those in group 1 of the periodic table have an oxidation number of +1, and those in group 5 have an oxidation number as -3. This is equivalent to the charge of the ions made. However, there are some exceptions. For example, hydrogen in metal halides has an oxidation number of -1. Oxygen in peroxides has an oxidation number of -1, and oxygen bonded to fluorine has an oxidation number of +2. It's worth noting that the sign goes before the number in oxidation numbers. In a compound, the sum of the oxidation numbers equals the total charge. So, for a compound, if the total charge is 0, we can use this to figure out the oxidation numbers of elements which we don't know. Roman numerals are used with elements that form ions of different charges. For the transition metals, the Roman numeral refers to the oxidation number. A redox reaction must have both an oxidation and a reduction occurring at the same time. We can use oxidation numbers to prove this. An increase in an oxidation number is called oxidation, and a decrease in an oxidation number is reduction. Chapter 5. Electrons and bonding. Electrons orbit the nucleus in shells. These shells are called energy levels. We call the shell number the principal quantum level, or simply n. The first electron shell can hold 2 electrons. The second electron shell can hold 8 electrons. However, unlike you were taught at GCSE, the third electron shell can hold 18 electrons. The fourth energy shell holds 32. The energy shells are further divided into subshells. The first energy shell, which holds 2 electrons, both have the electrons in s subshells. The second energy shell has s subshells and p subshells. An s subshell holds 2 electrons. A p subshell holds 6 electrons. In the third energy shell, there are s, p, and d subshells. A d subshell holds 10 electrons. In the fourth energy shell, there are s, p, d, and f subshells. An f subshell holds 14 electrons. So, the order of subshells is 1s, 2s, 2p, 3s, 3p, 4s, 3d, and 4p. Each subshell has a higher energy. However, there is an exception to this rule. The 3p subshell has a higher energy than the 4s subshell, meaning the 4s subshell will fill first. The order of filling therefore is 1s, 2s, 2p, 3s, 4s, 3p, 4p, 4d, 4f. A subshell can further be divided into orbitals. Orbitals are an area where there is a high probability of finding an electron. An orbital can hold 2 electrons, provided they have an opposite spin. Within a subshell, all orbitals have the same energy. 1 electron occupies each orbital before pairing starts. This prevents repulsion. For A-level, you'll be expected to work out electron configuration of atoms, up to krypton. The electron configuration shows how electrons occupy the subshells in an atom. For carbon, it has 6 electrons. We can have 2 electrons in the 1s subshell, 2 electrons in the 2s subshell, leaving 2 electrons for the 2p subshell. We write this as 1s2, 2s2, 2p2. If we're doing potassium, it has 19 electrons. So we have 2 in the 1s subshell, 2 in the 2s subshell, 6 in the 2p subshell, 2 in the 3s subshell, 6 in the 3p subshell, and we must fill the 4s subshell before we fill the 3d subshell. So, we can put the final electron in the 4s subshell. The configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. The periodic table is divided to show elements in each block. In the furthest left-hand side, we have the S block elements, the middle, D block elements, and the right has the P block elements. The bottom contains the F block elements. This refers to the subshell in which the highest energy electron is in. When forming ions, the highest energy subshells lose or gain electrons first. This does mean that the 4s electron is lost first before the 3p's electrons. So we must remember that the 4s subshell fills first and empties first before the 3d subshell. Ionic bonding is the electrostatic attraction between positive ions and negative ions in a compound. Ionic compounds form giant ionic lattices. These are closely packed in a regular structure. They have a high melting point due to strong attractive forces which require a lot of energy to break. Hence, they are solids at room temperature. The strength of the ionic bond depends on the charge of the ions and the size of an atom. An ion with a large charge and a smaller size will have stronger bonds. Ionic compounds are soluble, but only in polar solvents. This will be discussed further in a later chapter. Ionic compounds conduct electricity, but only when molten or dissolved in water. They do not conduct electricity when solid. This is because, when dissolved or molten, the ions are mobile and able to carry the charge throughout the compound. We can also use dot and cross diagrams to show the bonding in an ionic compound. Remember, a cation is positive and an anion is negative. Covalent bonding is the strong electrostatic attraction between a shared pair of electrons and the nuclei of the bonded atoms. The overlap of atomic orbitals represents a covalent bond. A double covalent bond is the shared attraction between 2 pairs of electrons and the nuclei of the bonded atoms. This is represented by a double line. We can also use dot and cross diagrams to show the bonding in a covalent molecule. Covalent bonding only occurs between two non-metals. A dative bond, also known as a coordinate bond, forms when a pair of electrons is provided by only one of the bonding atoms. It is represented in diagrams by an arrow. Average bond enthalpy can measure the strength of covalent bonds. The higher the bond enthalpy, the stronger the bond, and the more energy it takes to break. Chapter 6. Shapes of molecules and intermolecular forces. Pairs of electrons around a nucleus repel each other, so they move as far away as possible in order to minimize repulsion. We look at the number of electron-dense regions to calculate the shape of a molecule. An electron-dense region is where the electrons are bonded. This could be a single covalent bond or a double covalent bond. If there are two electron-dense regions around the central nucleus, a bond angle of 180 degrees is formed. This is a linear molecule. If there are three electron-dense regions around a central nucleus, it forms a bond angle of 120 degrees. This is trigonal planar. If there are four electron-dense regions around a central nucleus, a bond angle of 109.5 degrees is formed. This is tetrahedral. So far we have talked about bonding regions, but there could also be a lone pair. A lone pair repels more than a bonding pair. We subtract 2.5 degrees for every lone pair. A molecule with four electron-dense regions, one being a lone pair, is called pyramidal. It has a bond angle of 107 degrees. A molecule with four electron-dense regions, two of them being lone pairs, is called nonlinear, with a bond angle of 104.5. A molecule with five electron-dense regions around a nucleus can form a trigonal bipyramidal shape. It has two bond angles of 120 degrees and 90 degrees. A molecule with six electron-dense regions results in a 90-degree angle. It is an octahedral shape. You should be able to predict the shape of and the bond angles in molecules and ions with different numbers of electron pairs. It is worth becoming familiar with the bond angles, names of the shapes mentioned. You can be asked to draw the molecules in 3D. A solid line represents a bond in the plane of the paper. A solid wedge comes out of the plane of the paper. A dotted wedge goes into the plane of paper. This helps to create a 3D shape. Electronegativity is a measure of an atom's attraction for bonding electrons. It increases across the period and up the group. Fluorine is the most electronegative element. This means it attracts electrons the most out of any element on the periodic table. This is because as we go along the period, nuclear charge increases, so there's a greater pull on the electrons. As you go up the group, there is less shielding, meaning there are less electron shells. There is a greater pull, therefore, on the electrons from the nucleus. If two atoms have equal electronegativity, the electrons are held exactly between them. This is a non-polar bond. If two atoms have different electronegativity, a polar bond is formed. The ion with the biggest electronegativity has a negative partial charge. The ion with the smallest electronegativity has a positive partial charge. This is represented by the delta positive and the delta negative. A whole molecule is only considered polar if we take into account the shape of the molecule. If it is symmetrical and the dipoles all cancel out, then the molecule is non-polar. The dipoles here are referencing the delta positives and the delta negatives. Polar molecules are formed when the dipoles do not cancel out. Polar molecules can form strong enough attractions to ions to allow them to dissolve. This is because the ions in polar solutions have stronger forces than the forces between the ions of a solid. If we take an example of water, water is a polar molecule. This is because the oxygen is more electronegative than the hydrogen. We give the oxygen a delta negative sign and the hydrogen a delta positive sign. Water has two electron bonding regions. There are also two lone pairs around the oxygen atom. This gives water a non-linear shape. The shape is not symmetrical, therefore the dipoles do not cancel out, and water is polar. Carbon dioxide, however, is non-polar. This is because it takes a linear shape. This enables the difference in electronegativities between the carbon and the oxygens to cancel out. The molecule is symmetrical. Intermolecular forces are weak interactions between dipoles of different molecules. There are three: induced dipole-dipole interactions, permanent dipole-dipole interactions, and hydrogen bonding. Induced dipole-dipole reactions are also called London forces. The electrons in an atom are constantly moving around the nucleus. This means at times that there is an uneven distribution of electrons. This creates a dipole, a small negative charge, which induces a dipole in its neighbour. A few moments later, the electrons move and the dipole is gone. These are found in all molecules. As the number of electrons increases, the induced dipole gets larger. A chain reaction is produced in all of its neighbours. Another type of intermolecular force is a permanent dipole-dipole force. These are only found in polar molecules. They are much stronger than induced dipole-dipole forces, and they are formed due to the different electronegativities of the atoms. Simple molecular substances are made of discrete molecules containing a specific number of atoms. These form a simple molecular lattice. They have weak intermolecular London forces between the molecules, so they have a low melting and boiling point. These London forces are easily broken. They never conduct electricity because no charged particles can move from one molecule to another. Simple molecular substances are soluble in non-polar solvents. They are insoluble in polar solvents. The third type of intermolecular force is hydrogen bonding. Hydrogen bonding is the attraction between the lone pair of electrons in an oxygen, nitrogen or fluorine atom and a hydrogen atom on a neighbouring molecule bonded to another oxygen, nitrogen or fluorine. Hydrogen atoms in diagrams are always shown by a dashed line. Hydrogen bonding has a significant influence on the properties of water. For example, ice is denser than liquid water. This is because ice forms 4 hydrogen bonds in a tetrahedral arrangement. This creates an open lattice structure with large gaps between the molecules which lower the density. This allows solid ice to float. Water also has a relatively high melting and boiling point compared to other simple molecular substances. This is because hydrogen bonds are much stronger than London forces found in other simple molecular substances. There are many other properties of water caused by these hydrogen bonds. Another one you should be familiar with is surface tension. The molecules on the surface of water experience unbalanced hydrogen bonding. These unbalanced forces create a surface which allow insects to walk on the top. Chapter 7: Periodic Table and Energy. The periodic table has evolved over time. It used to be arranged by atomic mass. It was found by Mendeleev. He also lined up groups with similar properties, leaving gaps. This allowed him to predict the properties of undiscovered elements based on group trends. However, his periodic table did not contain the noble gases. Now the periodic table is arranged by atomic number. The vertical columns are called groups, and the rows are called periods. Across the periodic table, there are lots of different trends, with electron configuration, ionization energy, structure, and melting points. We know that in every group, they have the same number of electrons in their outer shell. Each period starts with an electron in a new highest energy level, e.g., the third row of the periodic table begins with the 3s subshell. You should also be reminded that the elements in the periodic table can be divided into blocks corresponding to the highest energy subshell. This gives 4 distinct blocks. Ionization energy can be defined as the energy needed to remove 1 electron from each atom in 1 mole of gaseous ions of an element to form 1 mole of gaseous 1+ ions. For example, sodium gas goes to Na+ gas plus electron. That's the first ionization energy. We've removed 1 electron. Na+ goes to Na2+ plus electron. This is the second ionization energy, as we have formed a 2+ ion. You need to be aware of the factors that affect the size of ionization energy. We have atomic radius. The greater the distance between the nucleus and the outer electron, the lower the nuclear attraction. Nuclear charge. The lower the number of protons, the lower the attraction between the outer electron and the nucleus. Electron shielding. Inner shell electrons repel the outer shell electrons. This repulsion reduces the attraction between the nucleus and the outer electrons. These factors allow us to establish trends going down groups and across a period. Going down the group, the atomic radius decreases. There are more inner shells, so shielding increases. Nuclear attraction on outer electrons decreases. Therefore, the first ionization energy decreases down a group. Across the group, nuclear charge increases. Each period has the same number of shells, so there is similar shielding. Nuclear attraction increases, atomic radius decreases, so overall the first ionization energy increases. However, as always, there are some exceptions. The first is beryllium and boron. There is a fall in ionization energy from beryllium and boron. This is because boron fills the 2p subshell, which is actually easier to remove than the 2s subshell of beryllium. The second is between nitrogen and oxygen. Nitrogen and oxygen both have electrons in the 2p subshell. However, in oxygen, 2 of the electrons are in the same orbital. These repel one another, making it easier to remove an electron from an oxygen atom than a nitrogen atom. You will often be asked to make predictions about the group of an element based on the successive ionization energy graph. There is a large difference in ionization energy between the shells. This is because it takes a lot more effort to remove an electron from a shell closer to a nucleus. If there is a big jump in ionization energies between the 5th and 6th electrons, we know the element is in group 5. If there's a large increase between 3 and 4, we know it's in group 3. One of the key trends in the periodic table is the move from metals on the left to non-metals on the right. Metallic bonding is a special type of bonding that just takes place in metals. It is the electrostatic attraction between cations and delocalized electrons. It occurs between 2 metal atoms. Each atom donates its outer shell electrons to form a sea of mobile delocalized electrons, which are spread throughout the structure. The cations are fixed in position, forming a giant metallic lattice. This gives metals some special properties. Metallic bonding is very strong, so it takes a lot of energy to break the bonds. This gives metals high melting points and boiling points. Hence, most metals are solids at room temperature. Metals aren't soluble, but can conduct electricity. The mobile electrons are free and can carry a charge around the structure. We previously found that covalent bonds can result in simple molecular substances. However, they can also result in giant covalent structures. The non-metals, boron, carbon and silicon, can form giant covalent lattices. They form a network of strong covalent bonds in a tetrahedral structure. The first we need to be aware of is diamond. It is made from carbon, with each carbon atom forming 4 covalent bonds. It has a high melting and boiling point due to the strong covalent bonds. It is insoluble in most solvents. It does not conduct electricity. The second we need to be aware of is graphite. Graphite is made from carbon, and each carbon atom forms 3 covalent bonds. This means that there is a spare delocalized electron, which allows graphite to conduct electricity. Chapter 8 is about reactivity trends. We first look at group 2 metals. These are called the alkaline earth metals. Each group 2 metal has 2 outer electrons situated in the s subshell. Redox reactions are the most common type of reaction in group 2 elements. Each metal is oxidized to form a 2+ ion. Another element can gain these electrons and become reduced. This makes calcium a reducing agent. Group 2 metals also form metal oxides, such as MgO. Group 2 elements can also react with water to form an alkaline hydroxide and hydrogen gas. The reaction becomes more vigorous the further down the group you go. Reactivity increases down the group. Group 2 atoms lose 2 electrons to form 2+ ions. This involves 2 ionization energies. Remember, ionization energy decreases down the group because the nuclear attraction decreases as a result of increasing atomic radius and shielding. The oxides of group 2 elements react with water to release OH- ions. They are only slightly soluble in water. When the solution is saturated, a metal hydroxide precipitate will form. The solubility increases of these hydroxides as you go down the group, so the resultant solutions are more alkaline. The lower the group, the more alkaline the substance. pH actually increases down the group, and that's a key fact. There are lots of different uses of group 2 compounds, and there are some that you should be aware of. Calcium hydroxide, for example, is added to increase the pH of acidic soils. Many indigestion tablets also use calcium and magnesium carbonate to neutralize stomach acid. The second group of the periodic table that we study are the halogens, group 7. They're the most reactive non-metal group, so they never occur in their elemental form. They are found as diatomic molecules, such as Cl2. Boiling points increase as you go down the group. This is because the number of electrons increases, making stronger London forces. More energy is then needed to break these London forces, so the boiling point increases. Halogens need to gain 1 electron to get a full outer shell, therefore they need to be reduced, and they can act as an oxidizing agent. Reactivity decreases down the group because atomic radius increases, there are more inner shells so shielding increases, there is less nuclear attraction to capture another electron from another species, so reactivity decreases. This allows us to do displacement reactions. Every element wants to be in a compound because this is where it can gain or lose electrons. If an element is more reactive, then it's more likely to be found in a compound, and the least reactive element can be displaced into a solution. For example, chlorine in a solution will react with iodide ions from a compound to produce chlorine ions in the compound and iodine in the solution. You should be able to write ionic equations, full equations, and half equations for all of these reactions. You also need to be aware of the colours of the halogens, as you will see these if the ion is displaced. Chlorine is pale green in water, bromine is orange, and iodine is brown. The colours can appear quite similar, so sometimes we add cyclohexane. This allows us to see a clearer difference between iodine and bromine. Chlorine is pale green in cyclohexane, bromine is orange, but iodine turns violet. Disproportionation is a redox reaction in which the same element is both oxidized and reduced. We can track oxidation numbers to show this. In the example, chlorine starts as a diatomic molecule, whereas oxidation number is 0. It goes to a +1 in HClO and -1 in hydrogen chloride. You do not need to remember this reaction, but you should be able to say when a disproportionation reaction occurs. We can also test to prove whether ions are part of our solution. To test for carbonate ions, we add nitric acid. You should see bubbling, or, if bubbling through lime water, a white precipitate forms. We then test for sulfate ions. We add barium, e.g. barium nitrate, a white precipitate will form. We then test for halide ions. We add silver nitrate. If chlorine is present, a white precipitate forms. If bromine, cream, and if iodine, yellow. It's hard to tell the difference as the colours are quite similar. Therefore, we add ammonia. Chlorine precipitates will dissolve in dilute ammonia. Bromine precipitates will dissolve in concentrated ammonia. Iodine precipitates will not dissolve. Then we can test for cations. The only cation we need to know how to test for is ammonium. To test for ammonium ions, we add sodium hydroxide and warm. If ammonium ions are present, a gas will be produced which can be detected by a damp piece of litmus paper. It will turn blue. To recap, the order of tests is carbonate, sulfate, halide, and then ammonium ions. Moving on to Chapter 9, we now look at enthalpy. Enthalpy is a measure of heat energy present in a chemical system. Enthalpy change is also denoted as delta H, and it's measured in kilojoules per mole. It's the amount of energy released or taken in during a chemical reaction. Exothermic means that energy is released into the surroundings. It is denoted as a negative energy change. Endothermic is when a reaction takes in energy from the surroundings. This is a positive enthalpy change. Enthalpy profile diagrams show the relative enthalpies of reactions and products. We need to look at the endothermic and exothermic enthalpy profile diagrams. For exothermic reactions, the reactants have more energy than the products. Therefore, they start higher up on the energy profile diagram. As the reaction takes place, energy is lost to the surroundings and the products are lower. Endothermic reactions are the opposite. The reactants have less energy than the products, as the energy taken in from the surroundings increases the energy overall. Delta H is shown here as the difference in energy between the reactants and the products. Activation energy, denoted as EA, is the minimum energy required for a reaction to take place. It's the moments where the bonds begin to break. We can show this on energy profile diagrams, with their difference in energy between the reactants and the highest amount of energy in the system. Enthalpy change always occurs under standard conditions. These are a temperature of 25 degrees Celsius or 298 degrees Kelvin, a pressure of 100 kilopascals, and all reactants in their standard states. We can measure enthalpy change using the equation Q equals mc delta T. Energy transfer equals mass of surroundings times specific heat capacity times temperature change. If you have calculated the energy transfer, you can divide this total by the number of moles of the fuel. This will give us the enthalpy change. If the reaction is exothermic, and you should be able to figure this out using the question, if this heat released is exothermic, you add a negative sign. If the reaction is endothermic, add a positive sign. However, our value we've calculated for enthalpy change will be different to the data book value. This is because heat has lost its surroundings in experiments. You may see the incomplete combustion of a fuel, you may see the evaporation of a fuel, and we may not perform the experiment under standard conditions. There are 4 different definitions for enthalpy change that you need to be aware of. First, there is the standard enthalpy change of reaction. This is the enthalpy change that accompanies a reaction in the molar quantities shown in a chemical equation. The standard enthalpy change of formation is the energy change associated with the formation of 1 mole of a compound from its elements. The standard enthalpy change of combustion is the enthalpy change that takes place when 1 mole of a substance reacts completely with oxygen. The standard enthalpy change of neutralization is the enthalpy change that accompanies the reaction between an acid and a base to form 1 mole of water. The value for all enthalpy changes of neutralization is minus 57 kilojoules per mole. Average bond enthalpy is the energy required to break 1 mole of a specific type of bond in a gaseous molecule. Bond breaking is endothermic, energy is taken in. Bond making is exothermic, and energy is released. There are some limitations with this though. When we're using calculations, we use the average bond enthalpy. The actual value may differ due to the different environments. The reaction may not be in a gaseous state, and therefore our values may be slightly different. We now come to Hess's law, which is a way of working out the enthalpy change. Hess's law states that if a reaction can take place in 2 routes, the initial and final conditions are the same, then the final enthalpy change is the same for both routes. We can use Hess's law to make a little triangle to show the different reaction routes. If they give us the standard enthalpy change of combustion in our question, we point the arrows down in our route. If they give you the standard enthalpy change of formation, we point the arrows up. We can use the given values to find the enthalpy change of the different routes, which will allow us to calculate the missing route. Remember, if we go against the grain of the arrow, we must flip the sign on the value. If we look at their example, there are 3 routes, A, B, and C. We're asked to calculate the enthalpy change associated with route A, which must be equivalent to B plus C. We are given the standard enthalpies of formation, therefore our arrows must point up. We can use the given values to find the enthalpy change for both sides of the overall reaction. We're travelling the route B plus C. However, we go against the route of the arrow B, so we must flip the sign. So we do negative B plus C. This gives us the enthalpy change of A. The final chapter is 10, Reaction Rates and Equilibrium. The rate of a chemical reaction is defined as how fast a reaction is used up, or how fast a product is formed. We can say rate equals the change in concentration divided by time. The gradient of a curve can also tell us the rate of reaction. If we draw a tangent at a specific given time, we can find the rate of reaction. The initial rate of reaction is the gradient of the tangent when t equals 0. Lots of different factors affect the rate of reaction. These include concentration, temperature, use of a catalyst, and surface area of solid reactants. We must use collision theory when talking about the rate of reaction. For example, when there is a higher concentration, there are more atoms of an element in a given volume. There are more collisions, therefore more likely to be successful, and the rate of reaction increases. If there is a higher temperature, kinetic energy increases, the particles move more, and there are more collisions which are more likely to be successful, which result in a higher rate of reaction. For a reaction to occur, the particles must have the correct orientation and an energy greater than the activation energy. We can monitor the progress of a reaction by measuring the removal of a reactant, for example, the change in mass as a gas is lost, or following the formation of a product, for example, collecting the gas as a product. A catalyst is a substance that changes the rate of a chemical reaction without undergoing any permanent change. The key definition that you should be aware of is that a catalyst provides an alternative pathway with a lower activation enthalpy. If we look at this energy profile diagram, we can see how the activation energy is significantly reduced with a catalyst. A homogeneous catalyst has the same physical states as the reactants. A heterogeneous catalyst has a different physical state from the reactants. It is a specific mechanism. The reactant molecules form weak bonds with the catalyst surface. This is called adsorption. Bonds within the reactant molecules break. New bonds form between the reactants. The product is released and leaves the catalyst surface. This is known as desorption. A Boltzmann distribution curve shows the spread of molecular energies of a gas molecule. The curve always begins at the origin, as no molecules have zero energy. The area under the curve equals the total number of molecules. The shaded energy shows the proportion of molecules with an energy greater than the activation energy. There is no maximum energy for a molecule. The curve will never meet the x-axis. You may be asked to draw a Boltzmann distribution curve to show how temperature affects the rate of reaction or how a catalyst affects the rate of reaction. For higher temperatures, more molecules have greater energy. Therefore, more molecules have an energy greater than or equal to the activation energy. A greater proportion of collisions will lead to a reaction, increasing the reaction rate. Collisions will also be more frequent as the molecules are moving faster. For a catalyst, a greater proportions of molecules exceed the lower activation energy. More molecules collide with the energy greater than the activation energy. There are more effective collisions and a faster rate of reaction. For higher temperatures, you will have to draw another curve. For catalysts, you will have to draw another line for activation energy. In an equilibrium, the rate of the forward reaction equals the rate of the backwards reaction. The concentration of reactants and products does not change. The system must be closed. You may remember from GCSE Le Chatelier's principle. When a system is in equilibrium and is subjected to change, the system reacts to minimize the extent of that change. For example, if the concentration of reactants increases, we form more products and equilibrium moves to the right. If the concentration of products increases, we form more reactants and equilibrium moves to the left. Remember, forward and backward reactions have the same magnitude of enthalpy change. However, one will be exothermic and one will be endothermic. An increase in temperature shifts the position of equilibrium in direction of the endothermic reaction. A decrease in temperature shifts the position of equilibrium in the exothermic reaction. You may prefer to write the equilibrium favours the forwards reaction or the equilibrium favours the backwards reaction. Change in pressure only has an impact when there are gaseous molecules present in the reaction. If we increase pressure, the position of equilibrium moves to the side with the fewer gaseous molecules. A catalyst, however, does not change the position of equilibrium, just speeds up the rate of reaction. The last thing we will look at today is the equilibrium constant. A reversible reaction can be written as follows. The lowercase letters represents the balanced number of moles, the stoichiometry of the equation. The equilibrium constant can also be referred to as Kc, and it is wrote as followed. The moles goes as the powers of the products or reactants, which are wrote in square brackets. Square brackets means concentration of. Therefore, to calculate Kc, we have to figure out the concentrations of the reactants and the products. They may tell you this in the question, or you may have to use the equation moles equals concentration times volume to figure this out. Kc tells us a lot about where equilibrium lies. If Kc equals 1, equilibrium lies halfway between the reactants and the products. If Kc is bigger than 1, equilibrium lies towards the products. And if Kc is less than 1, equilibrium lies towards the reactants. Thank you for listening. This has been Year 1 Inorganic Chemistry. If you found this useful, please like, comment, subscribe and share. If you're a little bit unsure on any of the concepts covered, please look out for my other videos where we will cover every topic in more depth. Keep a lookout as I will be posting Year 1 Organic Chemistry and Year 2 content very soon.